Newton's theory faced a challenge. The challenger was a doctor, Thomas Young. He was a total amateur in physics. But to understand this story, let's go back to where all of this began. In 1672, Newton used a prism to split sunlight. He concluded, white light wasn't pure. It's a mix of different colored particles. The reason was simple. Only particles travel in straight lines. Only particles bounce off mirrors. Only particles cast sharp shadows. But Robert Hooke, a leading scientist at the time, disagreed it. He argued that light must be a wave. He pointed to colors on a soap bubble. Waves can explain that kind of effect, but particles couldn't. Newton was angered by this kind of criticism. He then threatened to leave the Royal Society and even stopped publishing any optics work. Until Hooke died in 1703, Newton became the president of the Royal Society. Soon after, in the following year, he published his major work, Optics. With Newton's reputation, his particle theory became the accepted truth of physics in Britain. No one dared to question it. But Thomas Young was an outsider. He didn't care. He did a simple experiment. He shone light through two slits. Basically, if light were particles, Young would see two bright lines. Instead, he saw alternating bands of light and dark. When two beams of light met, they create darkness. Particles don't disappear, but waves can. It's just like waves in water. When a peak meets a trough, they cancel out and return to calm. Young thought he found the truth, but he underestimated the power of belief. Scientific community mocked him. He spent the rest of his life under Newton's shadow. But the debate was not over. To understand the light, the French Academy held a contest to settle it. The judges, led by Simeon Poisson, were supporters of the particle theory. They hoped to use math to attack it. In 1818, engineer Augustin Jean Fresnel submitted a wave-based theory of light diffraction. Poisson calculated it and deduced a ridiculous prediction. If light were a wave, then when shone onto a small disk, the waves should bend around the edges. They would meet in the center of the disk's shadow, and thus create a bright spot in the middle of a shadow. It is impossible, Poisson thought. He had proved the wave theory wrong. However, another scientist, Arago, tested it, and the physics world fell silent. There, in the center of the shadow, was a bright spot, Poisson's bright spot, which meant to disprove the wave theory, ended up proving it. Later, Maxwell used his elegant equation to confirm that light was an electromagnetic wave. It seemed Newton's particle theory was finally dead. Physicists celebrated. They thought they finally understood light. But they celebrated too soon. In the early 1900s, there came a new problem: the photoelectric effect. Shining violet light on metal knocks electrons. Red light does not, even if it's bright. This made no sense if light was wave. If light was a wave, its energy would depend on brightness. A bright red light should knock electrons out. In 1905, Albert Einstein had an idea. He saw the problem differently. Light might come in packets. These packets acted like independent particles. The inner energy of each packet was determined by frequency, a wave property. So the power of light depends on its color, not its brightness. Violet light has high frequency. Its packets are like heavy bullets. Red light has low frequency. Its packets are like small balls. Therefore, physics community was in an uproar. The particle theory was coming back? Physicist Robert Millikan spent a full decade trying to prove Einstein wrong. But ironically, his experiments ended up perfectly proving Einstein right. In 1923, he won the Nobel Prize for confirming the theory he tried to disprove. So now, physics community had a problem. Light seemed to be both a particle and a wave. What on earth is it? In 1924, Louis de Broglie proposed a philosophical answer. Why choose? If light can be a particle, why can't an electron, an atom, be a wave? Everything is wave and everything is particle. It sounded like nonsense. But soon, experiments showed electrons could act like waves too. Following this, Niels Bohr explained it this way. Light is both a wave and a particle. Which one you see depends on your experiment. Set up experiment to catch wave, like double slit. Then you see interference patterns. Set up to catch particles. Then you see particle hits. You can't see both at the same time. This infuriated Einstein. He couldn't accept this ambiguity and left his famous word, God does not play dice. But Bohr shot back, stop telling God what to do. This debate has brought humanity to the brink of a dizzying precipice. Perhaps light has never had any inherent nature. It is merely a cloud of possibilities. It travels through billions of light years away, like a dispersive wave, full of potential. But at the moment, it hits your eye. It has to act like a particle. It gives you its energy so you can see. To let you see, light changes from a wave into a particle. It's exactly this transformation that builds the world we see. You give light its destination, and so you take part in the creation of reality.